So this is for the 7.5 lesson from Michigan Virtual. It's called Discontinuities of Rational Functions. And the date is Wednesday, March 3rd. Okay, so we are going to start off with, obviously we have to know what that even means, but before we get to that, let's go ahead and start with we're going to start with what a graph of a rational function even looks like, because we haven't really seen one before. So here's what a sample graph could look like. Nothing, just a sketch. But what it is it's kind of going to have two curves like this. And they don't have to be specifically in these quadrants that I'm about to draw, but you can put them in kind of opposite quadrants like this. And then they're also going to have these things called asymptotes that we're going to learn more about on Friday. But there's these little dashed lines that we draw in. You've seen these before in Algebra 1, hopefully, with exponentials, but now we have vertical and horizontal ones that look kind of like that. So these are called asymptotes, but basically just from observations of this graph, we can hopefully see here that it's not continuous. The graph it's not continuous like how a parabola is or other lines and so on. Other families of functions that we've looked at have been fully continuous. This one kind of breaks up, right? So it breaks when it approaches asymptotes. And remember, we'll talk more about specifically the asymptotes on Friday. But for right now, this is just to kind of get us understanding what a rational function even looks like. So specifically, what these are called is these breaks or gaps are called discontinuities. Okay, so we are going to actually find these discontinuities. It basically is going to be like a jump in the graph or a gap or even a hole. Those are different ways to describe a discontinuity. Basically anything that's like not cohesive, continuous throughout. So to do that, we are going to start with the concept of domain. We've found domains and ranges even of different functions. We are going to start with domain of rational functions, so that it can help us as we understand these discontinuities. So basically, if you think back to what domain means, we know it means all possible x values in any function. And so it's easiest to see this usually when you see looking at a graph. If I was to even look at this sketch right here, I would say, what are the possible x values? Well, it looks like it's everywhere from the left because this arrow keeps going to the left. It keeps going, but then before it gets to like where I have my asymptote, let's say it's right on the y-axis here, then I would say it's not going to touch that y-axis. Then it's going to keep going for all my other x values because it starts back up right after that asymptote, and then it keeps going to the right forever. So it's basically like everything except for where the asymptotes are. So that's how we're going to kind of define our domains for these examples. Okay, so here's how we do that. We're going to be working with equations instead of the graphs, because I think equations help you see, you're going to see like more of the algebra with that. So our example here that we're about to get to is how do we identify the domain of the following rational functions. So I'll give you a couple of examples, like 3 examples of similar to what you would see on your quiz when you take your Michigan virtual quiz and test eventually, but how we're going to figure out the domain of these different rational functions that we're going to see here. So starting off with our first example, we have x squared minus 25 divided by x squared plus 6x plus 8. So again, it's just a rational equation like we've been seeing, rational function. We've been seeing these for some units now since the beginning of Unit 7. We've been seeing it consistently, and we want to figure out this domain. Well, if you think back to back from like even elementary school or middle school, probably middle school actually, where you learn about how anytime there's 0 in the denominator, that number is undefined. Okay, so that means that you can't ever have 0 in the denominator. Let me write that here, because this is important for whenever you're finding domains. Since the denominator, that's the bottom of the fraction, can't equal 0, or can't be 0, either way you think about it, because it's undefined. I'll put in that is undefined. Let's find what makes the denominator 0. Okay, we're going to find what makes this denominator equal to 0. So that's what you're going to do. When you see a problem, start off by setting the denominator equal to 0, like this. And then you would say, well, how would I go about solving this? Well, this is something we saw back in unit, I can think it was 2 or 3 in first semester, I think it was unit 3 actually. When you see this and you're asked to try to solve it, you have to factor it. So if you need to use the X method, go for it, or guess and check, where you need your 2 factors. This would be x plus 4 and x plus 2. Okay, because 4 times 2 makes 8 when you multiply them together, and a positive 6 when you add them together. So that's that. You can use that to help you. So if I know what those are my factors, let's go ahead and set them equal to 0 to solve. Feel free to do less work, but I'm showing all my steps here. You can do most of that, in your head even. So if that's my x is -4 and this one is -2, what this means is, for my domain, is that these 2 points, the graph would not be able to go through these 2 points because that would create 0 in the denominator. And if I have 0 in the denominator, I have an undefined function. So both of these, we want to tell the domain basically, don't go to these 2 points, go to everything else except for these 2 points. And so here's how we write what that means. So here it says, let's go ahead and write down our domain. This is the notation that's used. It's this little curly bracket, and then you write down what x can't equal. -4 and a comma, and then -2, and then you close that that curly bracket up. Okay, so it kind of looks like that. And specifically, if I was to write down what this means in words, this means that domain is all real numbers except -4 and -2. All right, let's try another one. So again, that was the answer on this one. Looks like this. And then let's try another one, same idea, but let's try a different type of equation. So let's say we have x squared minus x plus 2 divided by x squared minus 16. So again, to do this, you kind of ignore the numerator. You're not doing anything special with the top. You're just taking the denominator and setting it equal to 0. X squared minus 16 equals 0. You can solve this using square roots or factoring. So it's up to you how you want to do this one. I'll go ahead and solve it with square roots this time. X squared equals 16, square root it. We know that that's plus or minus 4. So again, that doesn't mean the answer is plus or minus 4. That means that when we write our domain, we want everything but these 2 answers. So here's how I can write my domain. I can draw the little curly bracket and write x not equal to 4, comma, -4. It does not matter which one you put first. And that's it. Let's do one more just so that you can hopefully get the idea that we have the last one here is going to be a little different. X squared plus 5x plus 6. But now let's divide it by x squared plus 4. So if I try to factor that bottom polynomial here, x squared plus 4. Let me show you what happens. So we have x squared plus 4 equals 0. I can't factor this. It does not factor anyway. I can try by square roots, but here's what's going to happen. I would get the square root of a negative number. And although that means i's, imaginary numbers or i's are introduced, I don't want to go there because we're not looking for imaginary solutions. We're just looking for what numbers would I have to substitute in here to make this 0. Well, there's no numbers. Okay, so if there's no real solution here, that means there are no numbers that will make this 0. That means my denominator, so I'll write here, since the denominator can't equal 0, The domain is all real numbers. It's everything. All real numbers. So this is the final answer. All real numbers is what you would have for this one. Now, on the quiz, it's all multiple choice. So again, you're just looking for these type of answers. For this one, it's just going to say the words, all real numbers. Okay, so then we move on to the next thing that Michigan Virtual's lesson goes into, which is called equivalent fractions. And we've been kind of working with these already, so it's not like brand new information. Equivalent fractions is where you start off with a question like, let me give you an example of a rational equation, and you were asked to simplify it. So if you were to ask to simplify x squared minus 6x plus 9 divided by x squared minus 2x minus 3, we would start by factoring it. So we'd factor the top and we'd get x minus 3, x minus 3. This is a perfect square trinomial where the two numbers that multiply to get 9 would be negative 3 and negative 3 so that you can get to negative 6 when you add them. And the bottom would be x minus 3 and x plus 1 because I want to, again, get two numbers to multiply to negative 3 but add to negative 2. That's what I would get. Now at this point, we know that when we see something on top and bottom, we can cancel it. So we cancel out one pair of those x minus 3's, and I'm left with x minus 3 over x plus 1. So this is completely simplified. So what we find out today is this idea of discontinuities, and what we saw with like the domain of this guy, what we would have been able to calculate, we would have said that the domain is anything except for 3 and negative 1. But you're actually going to see here that once I go further and find out that this domain is actually just it can equal negative 1, that it's a little different. This discontinuity is something a little different than what we saw earlier with the domain. Okay, so if we were to look at the graphs, we're going to look at the tables or the graphs of both the original problem and the final solution that I found, the simplified version. Okay, so this is the simplified version. This is the kind of original problem that I have. Let's look at the tables for both. And once we look at it, we're going to compare our values to see, are they the exact same table? Because maybe we think it should be since it starts off as 1 and it ends up as 1. But let's see what happens, because the tables I'm going to show you on the graphing calculator are very much the same, but let's see where it kind of is different. You don't need your graphing calculator for this, but just want to show you on mine. So what I did here was I divided the original problem, kind of wrote it out, x squared minus 6x plus 9 divided by x squared minus 2x minus 3. And then for the second equation, I wrote out the answer we got, which was x minus 3 over x plus 1. And if we go to our table here, and we look at the table starting at negative 2, you see 5 and 5. Then we see the error, like we said, at 1. I'm sorry, at negative 1, because notice it's in the denominator here. We can't have 0 in the denominator because it's undefined. That's why it's saying error. Keep going. You have 0, negative 3, negative 3. That's the same. At 1, it's still negative 1 for both. At 2, it's still negative 1/3 is the decimal that repeats. But then at 3, one of them says error and the other one says 0. And that's because at the original problem, at 3, that would have been a discontinuity, or there would have been an issue because you can't have 0 in the denominator, and 3 was creating a 0 in the denominator. But because it canceled out with the numerator, I now was able to see that my simplified version doesn't have a 3 in the denominator, or doesn't have x minus 3 in the denominator, which creates a hole there. So what this means is that, I'll write this in words. Actually, first let me just draw out a sample table so that you have something to refer back to instead of just looking at my calculator. So this was, x. We're going to pick the following x values: negative 2, negative 1, 0, 1, 2, and 3. You can choose to do more or less, but I wanted to make sure negative 1 showed up in there because you'll see how it was an error or undefined, and then the 3, how it was different for both. This middle column here, let's go ahead and put the original problem. Just rewriting what the original problem was. the x squared minus 6x plus 9, and the x squared minus 2x minus 3. And then finally, for this last column, I'll put our simplified version. That's what I typed into the calculator. So we don't always have to use graphing calculators for this. We can, or even just calculators. I'll show you how we can find these discontinuities eventually. Right now, we're just kind of understanding what happens here. So if I substitute in a -2, I got 5 for both. At -1, you get an error message, which means the same thing as it's undefined. So whichever way you want to write it, undefined or error. At 0, it was at -3 for both. And at 1, it was at -1 for both. And finally, at 2, it gets to -0.3 as a repeating decimal, or you can write it as -1/3. And at 3, this is where it was different. It was an error message or undefined, but then it became 0 for this one on the right. So this is telling me that the point 3, 0 is a point on this graph, on the simplified version, but on the original one, it's just an error message. I can't do anything there. Okay, so what this is telling me is that it's still undefined for this, but obviously 3, 0 is actually a point there. So what happens is, or what this means is that this means there is a hole, like an actual physical hole in the graph that you are going to show with an open circle. I'll show a sketch of this in just a second. And it's in the original graph. Now the graphing calculator will not show you this. You have to know that there is a hole there and physically draw it in if you were asked to graph at any point. It does not, the original graph doesn't actually pass through 3, 0 because it's not completely simplified for it to do that. And now the domains are different now too. So again, this is the reason this is happening is because we canceled out those negative, the x minus 3's, even though technically it wasn't going to work here on the original one. Because we canceled it out, it's no longer on the last one. And so that's why it's kind of appearing like it works. So that's why we consider it a hole. Okay, so this is how we write it. Since we canceled x minus 3's, you basically are removing, or we removed, the discontinuity at x equals 3. At x equals 3. Okay, and we will practice what this means. So let me tell you the definition of a removable discontinuity. And then I'll show you the graph for that one as well. So a removable discontinuity is basically a hole in the graph at a specific point. And it's removed because we canceled one or more of the factors. Okay, in this case, it was just one factor from top and bottom, the x minus 3, but you could technically do more than that. So here's what a graph looks like for this table specifically. If I just kind of do a sketch here, it was at -2 and up at 5. And specifically, I didn't get all the points on here, but it kind of looks like this curve, something like that. And then there would be an asymptote, which again, we'll talk more about tomorrow, at like this -1, and then also at 1, there would also be 1. But again, we'll talk more about that later because you won't know that right now. Then the rest of these points at 0, it's at -3. At 1, it's a -1. 2, it gets even closer to -1/3. But then at 3, this is where there's confusion. 3, 0 is going to have a hole in it. So I can put like a little hole here when I draw out this curve. Okay, so it's kind of like this kind of curve, but there's this like open circle that's like a hole basically sitting at 3, 0. That point is 3, 0. Now the reason it's 3, 0, we of course got that from the table, but here's what we could have done if we didn't have a graphing calculator or calculator handy. We could have taken 3 and substituted it in for your original problem. So if I was to substitute that back in, we would do 3 minus 3, 3 plus 1, that's 0 over 4, which is 0. That's where we're getting this 0 from. And then you can write it as an ordered pair, saying that that is called the removable discontinuity. Because we're going to practice some questions on that right now, where it's going to say, what are the removable discontinuities? Well, it's 3, 0 for this one here. We have to factor it. You have to cancel what cancels out. And the thing that's canceling out is your x value, which in this case is 3. And then you plug that 3 back into the original or to the simplified version so you can find your y value. So let's try a few of these out so that we get some practice on this. So our question here, we'll do 2 of them together. Identify the removable discontinuity, or which, remember, that just means like a hole, of the following. And our first example will be, obviously we did one earlier, that one was one example. Here's the next one, x squared minus 16 over x squared minus 9x plus 20. So when you see a question, you want to first start by factoring it. So we have x minus 4, x plus 4. The bottom would be x minus 5, x minus 4, because they have to multiply to get to 20, but add to get me negative 9. At this point, you have to figure out, what am I going to cancel out? So whatever you choose to cancel, or whatever is canceling, that's going to be where the removable discontinuity would be. So at x equals 4, because that's, if you need to solve it, you can show x minus 4 equals 0, and adding 4, you get x equals 4. And then from there, let's see what's left over. X plus 4 over x minus 5. You want to take this answer that we got, the x equals 4, and substitute it back in for both those x's. So we have 4 plus 4 over 4 minus 5. That's 8 over negative 1, or negative 8. So I would write my final answer for the removable discontinuity. It's going to say, where is it? What is it? It is 4, because that was the x value we canceled, negative 8. You would write it as an ordered pair, and these are going to be, again, multiple choice questions on the quiz that you can look for. Where is that correct choice? So again, find it by whichever one you canceled it. Always switch its sign though. Don't keep it, negative 4 like this one was. It was 4. Then plug that number in to the final simplified version to find out what is the final y value of the discontinuity. That means there would be a hole if you were to graph this at 4, negative 8. All right, let's try one more, and then we'll be all set here. X squared plus 5x plus 6 divided by x squared plus 9. So for this one, you're going to start off by factoring. So we have the top factors as x plus 2, x plus 3, but the bottom does not factor. Kind of leave it at x as x squared plus 9. We can say does not factor. Because remember, it has to be x squared minus 9 for it to factor further as x squared, or x plus 3, x minus 3. This is a sum of two squares, which we don't factor. We don't know how to factor that further, or it doesn't factor any further. So we would say that there is no removable discontinuity on this one, because there's no canceling out that we have to worry about. It also has all real numbers as the domain, if we remember back from the first example, or the first few examples, but specifically it has no removable discontinuity. You, on a question on the multiple choice, I think it's going to say none of the above, basically. So I'll just put that also as an answer. Because although there's no answers here, if I did have a list of multiple choice options, none of them would work because there's no removable discontinuity here. All right, so if you have additional questions or any questions on this, please make sure you email me or use the Google form, and then we'll go over a lot of it on Friday. If you have questions before then, though, I can meet via Zoom. Have a great day.